Sure.
Just a couple of seconds until it picks up on YouTube. There we are, all set. So good evening, everybody. This is a pleasure to be inviting, Dr. Aru Beri from IISER Mohali for giving us a talk on this very interesting special day of International Day for Girls and Women in Science, which is a very important topic. And Aru and me happen to be working on this particular issue at the national level through the Gender in Physics Working Group. So that's where I know that she's passionate about not just astrophysics, but also about gender issues in physics. So I couldn't think of a better person than her to be addressing today. And we have already had Prajwal talk to us both about astronomy and gender previously. So it's most appropriate that we have Dr. Aru Beri with us today. And VINN for Aru is the Tamil word for space. So our club is called VINN, which simply means space. And, this is our little effort in trying to ensure that Tamil Nadu has some traction in astronomy and astrophysics, because we were sorely lacking for the longest time. So without any further ado, I request Asmita to take over today's talk. And thank you, Aru, for accepting our invitation.
A very good evening to all. So today, on the occasion of International Day of Women and Girls in Science, VINN Astronomy and Astrophysics Club, Central University of Tamil Nadu, is glad to organize a webinar on this topic, exploring stellar remnants after lives of stars. So when we talk about this day, the importance of this day, we know that women are pretty much less represented in the field of physics, maths, etc., like STEM research fields, because of a lot of biases towards them and the gender stereotypes exist in the society. So to stop all these biases, we are celebrating February 11th as International Day for Women and Girls in Science. This year with a theme, Equity, Diversity and Inclusion Water Units, to ensure an equitable treatment for women and to make them inclusive of all the fields of science and not to lose their talents towards the field of science, right? So I am pleased to invite respected Dr. Aru Beri ma'am, who is our speaker today. She is an eminent women scientist, as Madhurima ma'am said, an X-ray astronomer, and a professor at the IISER Mohali Department of Physics. She has specialized in the fields of high energy astrophysics, X-ray astronomy, X-ray binaries like neutron stars and black holes. Also carried out several campaigns to study these stellar objects. She has completed her studies from IIT Ropar and was a postdoctoral fellow and a Royal Society Sir Newton International Fellow at Southampton University, UK. She has multiple publications in her name. So we are glad to invite you, ma'am. Welcome you, ma'am. We are also glad that we got Dr. Madhurima ma'am as our faculty in charge of VINN Astronomy Club, who is also an inspiring woman physicist and leader in our university. Welcome you, ma'am. I extend heartily welcome to all of the faculty members, students, and coordinators who have joined here. Welcome you all. I kindly hand over this session to Dr. Aru Beri, ma'am.
Thank you. Thank you, everyone, for inviting me. It's a pleasure to be here and really happy to give this seminar during this special occasion. So I'll start with the talk now. So as you can see, the title of the talk is Exploring Stellar Remnants, Afterlives of Stars. So these are some sort of special stars or dead stars, usually we call them, which we often call it as stellar remnants, and we will be walking through what sort of stellar remnants are of interest to me and how do we study and things like that. So as I mentioned, they are called dead stars. So before we talk more about how these stars are formed and so on, let's try to have some analogy of with the life of a butterfly. So in this slide, let me turn on my laser pointer. So if we know about the life of a butterfly, it starts with the egg and then it goes into caterpillar phase and then to the pupa, and finally it blooms as a butterfly. And if you look at the life of a star here, and so we by now we all know how stars are formed. So they are usually formed from the dense clouds of gas and dust, which are nebula. So they are star forming nebula, and they on compression and compression under their own gravity, they form a stars, and the cycle starts with the protostars, and those goes into sun-like star or main sequence stars, we call them. So all sun-like stars are formed from these clouds or star-forming nebula, and then they undergo their life cycle and reach a stage of red giant. And during this phase, there is, as the name suggests, they expand in their sizes, and finally they burst out as planetary nebulae. I'll explain you briefly what planetary nebulae is. And then after this phase, you essentially the star turns into a white dwarf, or which is a dead star. So this is basically end products of the life cycle of a star. So white dwarf, again, this is a very compact star where you do not have a fuel within the star itself to sustain it against the gravity. So there should be an equilibrium between the gravity and the radiation pressure, which is the pressure which is created because of the reactions of the fusion reactions within the star. So that balances, and until that balance is there, the star is living happily. But once the fuel is depleted, it contracts under its own gravity. And when it basically contracts under its own gravity, so the outer layers of the star basically explodes, and this phase is known as planetary nebulae. Now, this whether the star will turn into a white dwarf or a neutron star or a black hole, which all these three stars or three types of stars are known as death stars. So what will be the fate of the star depends upon the initial mass of the star. So whether the star is very massive or not that massive, or a sun-like star. If it's a sun-like star having a mass of almost the mass of the sun, or similar, equivalent to the mass of the sun, then it will result into a white dwarf. But if it's a massive star, then the life cycle of star is something like this. So you form a star, there's a protostar stage, and then there is another giant phase in the life cycle of the star, which is known as red supergiant. And after this phase, again, there is an expansion of the outer layers, and then you basically explode the star in the supernova stage, and we'll see a short movie also in the later slide. So in this supernova explosion, which are the most massive and the most luminous explosion in the universe, results into the formation of the compact objects or the dead stars, which are known as neutron stars or black holes. So very massive stars turn into neutron star or black hole, while less massive star results into a white dwarf star. Again, this is a artist impression or showing, as I previously mentioned, about the hydrostatic equilibrium. But by hydrostatic equilibrium, I mean the star is able to sustain itself against its own gravity because of the fusion reactions, which results into a radiation force. And that radiation force and the gravitational force balance each other, and thus star sustains itself during its life. While when this pressure the fuel, which is basically hydrogen converting into helium, which releases energy. Once this hydrogen is depleted within the star, that results into a contraction within its own gravity, because now there is no additional fuel to sustain itself against gravity. So this is a bit simplistic picture of the same thing which we have seen earlier. As you can see, the stars formation starts from the nebular phase, and then you get an average star or a massive star. And then based upon the initial mass of the star, the phase of the next phase of the star depends upon the initial mass, whether it will be a red giant or red supergiant, and then the explosion, whether it will be planetary nebulae or a supernova explosion, which will finally result into the dead stars, or they are also known as compact objects. And I will explain you why they are called as compact objects in my presentation. So before that, as I mentioned, the planetary nebulae, so when red giant basically dies, the heat and pressure from its core ejects the outer layers of the star into space. And these outer layers became known as planetary nebulae. And this is a short movie of showing a supernova explosion. Okay. Okay, so since you have watched this movie now, can you imagine how much energy is liberated when the supernova explosion takes place? I mean, if I'll be happy if you can answer over chat box if you are not able to unmute yourself due to permission issues. I mean, just imagination, how luminous do you think the supernova explosion can be?
There are no permission issues, but they might have internet issues. So chat box is always an option.
So any number that clicks your mind or anything? Or in comparison to sun, can you imagine how much luminosity can be liberated when the supernova explosion takes place? Okay, so if you just compare with the sun's luminosity, the light or the energy released by the sun, what we receive from the sun is of the order of 10⁻33 ergs per second. And if you compare the energy released in the supernova explosion, it is of the order of 10⁻43 ergs per second. So they are extremely luminous, or they outshine the universe itself. And these are very exciting phenomena or events which takes place in our universe. And can you imagine if there is no supernova explosion taking place on our universe, then how will be our life be? So can you have some rough imagination of our life without a supernova explosion? Okay, so to give you some idea about supernova explosion, before we talk about the life without supernova, I'll just give you an imagination. So basically in this phenomena, what you happen is, as I mentioned, it's basically the contraction of the star under its own gravity. And this massive star, which is 5 to 10 times massive than the mass of the sun, when it contracts under its own gravity, this process this process actually takes place within a few seconds. And within that seconds, as you can imagine, a very massive star is undergoing an implosion event. So the outer layers of the star, there are shocks which are formed, and that expels the outer layers, and hence the explosion takes place. And the core, which is remaining or contracting within its own gravity, results into a neutron star or a black hole. So this is how a neutron star or a black hole is formed. And during this explosion process, what happens, since it's a massive star, so unlike a sun-like star where you only have a hydrogen which fuses to helium, we do have massive elements also being formed in the nuclear fusion reactions within the star. So when the explosion takes place, all the elements which are formed, or nucleosynthesis process, which we call as in scientific terminology. So that nucleosynthesis process results into heavier elements and that are exploded into the universe or the sky when this event takes place. So just to give you an idea about the basic elements in the universe originated in Big Bang, you have hydrogen and helium. And so if you have a sun-like star, the fusion reactions can result into nitrogen or carbon-like elements. And when you have a massive star where the supernova explosion takes place, you have a whole range of elements which are formed during the life cycle of the star, which is finally exploded into the sky. So all these elements which you can read here, like aluminium, calcium, carbon, chlorine, copper, etc. So these are the elements which you will also find that we use it in our daily lives in some or the other way. So as an example, for your computers and cell phones, you basically use silicon, carbon, hydrogen, oxygen, sulfur. So all these elements are produced during the supernova explosion. So without a supernova explosion, you'll be kind of deprived of all these elements which are now used for our own daily lives. So these are important and the rare events taking place in our universe. And I mentioned you earlier in my presentation that we call neutron stars, white dwarfs, black holes, not only dead stars, dead because we do not have a nuclear fuel to sustain itself. I mean, as you by now understand, we do not have a nuclear fuel which will cause a fusion reaction for the star to sustain itself against its own gravity. So they are dead stars. We do not have a fuel. It's the end life of a star. And on the other, on the same scenario, we also call it as a compact object. So why compact objects? Because of the small size of these stars. Unlike a sun-like star or a star which is massive star, you have the star can be like few times or few hundred times the size of the sun as well. But in this systems, if you compare the radius of these stars here, if you take sun as a reference, you have a mass of a sun, which is given by m sun, or this is basically a representation of mass of a sun and the radius of the sun, and take it as a reference. So you see the white dwarf is less than a mass of sun, whereas neutron star has a range of mass, which is 1 to 3 solar mass. And while the radii, if you compare it with the radii of the sun, it is 10⁻⁵ times the radius of the sun. So you see that a huge density is compressed within a small size of the star. And that's why they are compact, or compact in size, or also called as compact objects. Similarly, black holes. So in the case of black holes, actually there is a classification of black holes based upon the mass of the black hole. We'll not go into those details, but I mean, just here it is mentioned as arbitrary, but you can have a mass of a black hole of size, mass greater than 3 solar mass. It can be a few billion times solar mass as well, which are known as supermassive black holes. While if you compare the radius, you have something known as Schwarzschild radius, which is given by 2gm by c square. We'll go into these terms later in my presentation. While the density is proportional to your mass upon the size of the star. And where the surface potential, which is basically the gravity, effect of the gravity, which is huge compared to the mass gravity on the surface of the sun. So coming to the white dwarf stars, which is the first type of the stellar remnant, or stellar remnant, which is found from the sun after the end cycle of the sun-like star. So this is on the left top, we have a pictorial representation of a white dwarf star. And this is on the top right, we have a sun when it turns into a white dwarf. So which is like 6 billion years from now. This is how the sun will, because the sun will eventually become a white dwarf. And now, as I mentioned, you do not have a fuel within the star to sustain itself against gravity. Then what sustains them against its own gravity? Why don't they further compress and just become a point, or have a zero size or something like that? So what sustains itself against its own gravity? So I'm sure with your basic physics courses, you might be familiar with something known as degeneracy pressure. Or to explain it in a very simple terms, you can you imagine a parking lot, and in that parking lot you have, if it's all empty, all the cars are placed well in their assigned lots. But if it's if you have a parking lot which has less number of spaces, a few spaces available, while the number of cars are very large or are increasing, then you have basically a race or a fight that who will get the parking lot. Now, if we take that as an analogy to the electrons which are there in the white dwarfs, you know the Pauli exclusion principle, and basically electrons or fermions to follow that Pauli exclusion principle. And so something like that, they will have their own energy levels being occupied. But when you have large density of electrons available within the star, then it's something similar to have less spaces available, but more number of cars there in the parking lot. So then there is sort of a, and you know that fermions have to follow the Pauli exclusion principle. They cannot occupy the same energy level. And then there's sort of a pressure generated or by these electrons within the compact object. And this pressure, which is known as degeneracy pressure, basically sustains the compact object against its own gravity. And hence, and the similar phenomena also helps in the case of neutron star to sustain against its own gravity, but while in the case of neutron stars, we have neutrons, which are helping out or kind of contributing to the degeneracy pressure to help it sustain against its own gravity. So I mentioned about neutron stars. So let's walk through a brief history of neutron stars. Well, today on this occasion, it has to be done basically because they were first time discovered by a woman scientist, which is who is Jocelyn Bell, who was a PhD student. And in 1967, for the first time, when neutron stars were observationally found. However, in 1933, there were proposed existence of neutron stars. So Walter Baade and Fritz Zwicky were the two scientists who actually proposed theoretically that there is an existence of something called as neutron stars in the universe. However, the observational evidence of the existence of the neutron star was found in 1967, when Jocelyn Bell, being a PhD student, was trying to observe in radio the radio sky. And what she found was in this image, as you can see, there is some, it's a sort of a graph where she was recording the signals from the sky, and she saw a sort of periodic signals which were coming at regular intervals. And that was very peculiar at that time, and it was sort of a strange signals. Nobody could immediately understand why such so periodic signals are observed in and throughout the day. So this was a source which was discovered when Jocelyn Bell was studying or doing her observations. So the source is now known as PSR B1919+21. And the pulsations which were recorded were at intervals of 1.337 seconds. They were extremely regular pulses. So as I mentioned, it was peculiar and strange to see such periodic signals in the observed. And so there were possibilities which were what could be the source of such periodic signals. So one of the possibilities they were thinking about was some sort of alien signals from the other universe, and which is also known as little green men. And the second possibility is there are some rotating compact objects. It can be a white dwarf or a neutron star. But now, why the possibility of neutron star turn out to be winning over white dwarf? Because of this condition, which is you have a minimum period of the compact or the star, which is limited by the centrifugal acceleration at the equator should be less than the gravitational acceleration. So if you do these calculations, put in the numbers of the density of the neutron star and the density of the white dwarf star, so the winning outcome was for the neutron star. So hence it was confirmed that it is a neutron star being discovered during these observations. And this is a short video by Jocelyn Bell herself explaining her experience while discovering these class of objects. And that is a major discovery in the field because that led to a new sort of science or the driving in finding more such neutron stars, more pulsars in the radio sky, and also like further leading to other discoveries in the field.
That bit of the sky due to go through the telescope beam at 2 o'clock, 3 o'clock in the morning, December the 21st, perishing cold. And I switched on the high-speed recorder and it came blip, 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 blip. Clearly the same family, the same sort of stuff. And that was great. That was really sweet. It finally scotched the little green men hypothesis, because it's highly unlikely there's two lots of little green men, opposite sides of the universe, both deciding to signal to a rather inconspicuous planet Earth at the same time, using a daft technique and a rather commonplace frequency. It has to be some new kind of star, not seen before. And that then cleared the way for us publishing, going public. Martin Ryle called up the editor of Nature, John Maddox, and more or less said, we've got something interesting coming. He didn't quite say hold the presses, but he nearly did.
Now, the people here say that if they got 3 signals as exactly spaced as that, it would be very unusual. If they got 4, it would be phenomenal. Well, they've had pulses as exactly spaced as that 24 hours of the day since November.
Well, these signals that we're picking up are entirely new. Nothing like this has been seen in radio astronomy before.
The excitement was because this was a totally unexpected, totally new kind of object, behaving in a way that astronomers had never expected, never dreamt of.
Okay, so as you have watched this video and see the excitement of the new discovery in the field, and this is how the pulsars were discovered in the sky. And as by now you have heard several times, a few times, that they are periodic signals, and this is how the pulsations basically look like. So you have an intensity on the y-axis and the versus time. So intensity is periodically showing a trend, which is separated, the two peaks are separated by the P, which is the period of the star. And in this case, it is a 1 second periodicity, and the regularity of this, by regularity, I mean the rate of change of your spin period of the neutron star is of the order of 10⁻⁶ seconds per year. So you can see that how this precise this number is, and hence they are also known as perfect clocks or in the sky. So highly periodic signals from the X sky, and this is an artist impression of a pulsar. And so basically this is a neutron star, and you have charged particles surrounding these neutron stars, and you have a rotation axis, you have a radiation beam. Basically this is a line of sight, and you have a magnetic field axis as well of the neutron star. And due to the misalignment between these three axes, you basically see the periodicity in the signals, which is sort of this behavior which we observe in the observational astronomy. So giving you shouldn't be scared of a lot of calculations here. They're very simple. So to understand how pulsars illuminate or release energy. So basically it's the rotational energy in this case, which is the main source of pulsar energy, or the light which we observe from the pulsars. So the E rotational energy, which is given by I omega square, where omega is your rotational frequency of the neutron star, is the source of energy here in this case. And if this is the source of energy, you can imagine when the star radiate or the neutron star radiate, it's also angular momentum is transferred from the neutron star here in releasing this energy, and hence it's also slowing down. So if you want to find out the rate of change of your spin period of the neutron star, basically you observe it and observe the luminosity illuminated by the neutron star. And then you can, from this expression, which is the rate of change of your energy or the rotation energy, which is equal to the luminosity, which is the observable, you can measure the rate of change of your spin period of the neutron star. So the previous class was a specific or a special class of the pulsars, where the rotational energy is responsible for the release of the energy, or the energy which we observe in the radio sky. But there is another class of pulsars. By pulsars, again, these are neutron stars which are rotating neutron stars. And you have another class of pulsars which are also known as X-ray pulsars or X-ray binary systems. And these X-ray binary systems, you have a neutron star or a black hole sitting at here somewhere. You see there is a beam of light or some sort of jets coming out in this image, and the compact object is sitting at the center of this. And then you have a massive star which is here, or it can be massive or a sun-like star, or it can be another main sequence star, which is a companion star to this compact object. Now, if you remember, the rotational energy is causing the release of energy in the previous class of pulsars. Here, the release of energy is because of the mass transfer from the companion star, where the companion star can be a main sequence star or any sun-like star. Because these are compact objects having a strong gravity, so they can attract or pull the matter from the companion star. And when they, because of the strong gravity, they pull the matter from the companion star, basically they form a ring-like structure or a disc-like structure around these compact objects. So please do not get confused if I often used a term known as compact object, because this is a general picture of a X-ray binary, which are the special class of objects where, as the name suggests, it's a binary system where you have two stars in composing a system, and one of them is a main sequence star while the other is a compact object. And compact object can either be a white dwarf, or it can be a black hole, or it can be a neutron star. So the disk which is formed around the compact object is the basic engine of the generation of the light, or the basic mechanism of the emission of your or the light which you observe from this class of objects. So it's called as a also known as engine of the emission in the case of X-ray binaries. And because of the angular momentum or the gravitational energy release, so they have the question arises, when the matter is falling onto these compact object, why does it forms a ring around this compact object? So the ring is formed because of the angular momentum conservation. So it has a huge angular momentum, the incoming matter, so it directly cannot impinge onto the compact object. So how it basically balances out its angular momentum is by forming the circular disk of circular rings around the compact object. And the mass which is falling onto this compact object, or the gas which is falling onto this compact object, can be extremely hot, of the order of 10⁶ to 10⁸ Kelvin. And you can imagine these temperatures are extremely hot to radiate. And this radiation is what we observe in the X-ray sky. So now in comparison to the radio sky, these are the objects which are most bright in X-rays. So you have a different sort of electromagnetic spectrum which is covered by these range of this class of objects. You have a radio emission from the isolated neutron stars or pulsars, where your mechanism is because of the charged particle around the neutron stars are helping out in the energy release, where in this case you have the mass transfer from the companion star causing the energy release. And these are more brighter in the X-ray sky, while the other previous class is bright in the radio band. So again, to explain you more about this this class of pulsars, you have a neutron star which is shown here in the top left in blue. And then, as I mentioned, you form an accretion disk around this compact object. And since this neutron stars have high magnetic field, and the magnetic field can be of the order of 10⁻12 Gauss. And this is huge magnetic field if you compare this magnetic field with the magnetic field of the Earth. So do you know what is the magnetic field strength of the Earth? Just imagine compare it with the magnetic field of the Earth, and then you will realize that how strong is the magnetic field here in the case of neutron stars. And this huge magnetic field is basically channeling the matter from the accretion disk onto the poles of the neutron star. So it's not spreading throughout the neutron star, but it is falling onto the poles of the neutron star. And then you, as I mentioned earlier, that you have a rotation axis, you have a magnetic field axis, and you have a line of sight. So basically this misalignment between the three axes is releasing the pulses which we observe in the, whether it's a X-ray sky or a radio sky. And so, as I mentioned, they're strong magnetized objects. And now you would like to know that what is the extent up to which your magnetic field extent of the neutron star can be filled by the incoming matter. So how do we get to know that what is the extent of the magnetosphere of around these neutron stars? And one can ideally calculate or evaluate that from the observables, which basically we do it from observations. So you have magnetic pressure because of the magnetic field of the neutron star, which is given by this expression where these terms are well known. It's a magnetic field, and then you have magnetic moment if you convert your magnetic field in terms of magnetic moment and so on. And then you have a gas pressure, and this gas pressure is which is given by rho v square, where v is the velocity of the incoming gas and rho is the density of the gas which is coming. So if you equate these magnetic pressure it's an ideal world calculation, because there can be another shocks or another way of where you are losing your incoming gas and things like that can happen. But ideally, you can measure the extent of the magnetosphere by balancing this magnetic pressure with the gas pressure because of the incoming gas. And then what you get is the Elfman radius or the magnetospheric radius. And if you observe this particular expression here, you can imagine or assume a neutron star with a fixed magnetic moment, and then also the mass of the neutron star, considering it to be a solar mass neutron star. If you see, there is a term which is known as m dot. And what is this term, m dot? This is basically rate of change of mass transfer. So rate of change of mass transfer is a basic observable, which is the term leading the extent of the magnetosphere around the neutron star in the case of accretion powered X-ray pulsars. So there is a term which is known as accretion luminosity, and which is given by GMM dot by R star. So given a fixed neutron star with a fixed value of GM mass of the neutron star, the variable is m dot, which is mass transfer. Now this mass transfer will vary because your companion star may lose lose mass at a particular rate at particular instant of time. So these are variable objects, which shows a lot of variability as you observe them in long intervals of time. So m dot can change. And this accretion luminosity is observable. When we do observations, we basically measure the luminosity illuminated by these objects, radiated by these objects. So when you measure the accretion luminosity, you get a measure or a hold of m dot. And once you evaluate that m dot, you can get the value, extent of the magnetospheric radius. So if and you see the power is -2/7, which means if your mass accretion rate is higher, then you will have a larger magnetospheric radii. But if, if your mass accretion rate is higher, since it's an inverse term, your RM will be smaller. So basically the Elfman radius will be closer to the neutron star. When your m dot is lower, then your RM will go beyond the neutron star. And what is the role of this Elfman radii? As I mentioned, that it's a magnetic strength or a magnetic field of the neutron star, which is channeling the matter onto the poles of the neutron star. So if your RM is smaller or close to the neutron star, basically the pull to the poles of the neutron star will be stronger. Means your more mass will be accreted onto the poles. But if your RM extent of the magnetosphere increases, basically the strength of the magnetic field on the incoming matter will decrease. So you have low luminosity, which is observed. And this observable, which is a mass transfer, plays a very important role in the case of accretion-powered X-ray pulsars. The reason being, as I mentioned previously also, we could measure the rate of change of your spin period or spin frequency of the neutron star if you measure the luminosity in terms of energy released from the rotational energy. But in this case, the mass transfer is the variable which is to be evaluated, and that can help us in understanding the rate of change of your spin frequency. And here in this expression, you can forget about rest of the terms because they assume to be constant for a neutron star, where they have their own standard terms like mass, radius, magnetic moment, moment of inertia, and so on. The variable here is the accretion luminosity, which is here given by L37. So this accretion luminosity, as I already mentioned, is given by GMM dot by R star. Again, rest of the terms are constant, but M dot is the variable. So if you measure the luminosity, you can actually get hold of the rate of change of spin frequency of the neutron star in the case of accretion-powered X-ray pulsars. Now, as I mentioned about observational astronomy, that this is a variable which we measure. It's not only about the luminosity which we measure, but there are other sort of variety of things which we do in astronomy, and one of them is pulsophiles. So I'll show you what I mean by pulsophiles. But before that, let me explain you what is being shown here in this plot. You have a neutron star. As I mentioned, the matter is channeled onto the poles of the neutron star. And now if you see the matter is coming onto the poles, it just forms like a column or a cylinder over the above the surface of the neutron star. And as the density of the incoming gas is different at different heights of this column or the cylinder, which is formed above the neutron star, then you basically the radiation which is coming out from the neutron star surface, because this incoming matter is releasing the energy, the gravitational energy release is observed in X-rays. And now the radiation which is released from this hotspot or the neutron star surface basically interacts with different heights of this column. And when this interacts with the different heights of the column, basically, it can undergo sort of modification, because when it interacts with the matter, it can undergo different processes like absorption, scattering, and light bending because of the gravitational effect of the neutron star. And all those phenomena can basically modulate your signal. You can imagine something like electronical signals which can get modulated. Something of the same sort is happening with the radiation or the signals coming from the neutron star. So some sort of modulation can happen in this cylindrical height, which is above the neutron star. So as I mentioned, I'll explain you what pulsophiles are. So this is an observational result, which was published in 2014, and these are the pulsophiles. So if you see the y-axis here in this plot, which is on your right panel, you see y-axis labeled as normalized intensity. If you just forget about normalized, because I just normalized it with respect to the average intensity. So it's basically giving you the counts per second information, or the rate at which the counts are being recorded by the detectors or our X-ray observatories or X-ray telescopes. And on the x-axis, you have something called as pulse phase. Now, a very simple mathematical calculation. You have a period of the neutron star, and you can easily convert that into phase information, because you have a time information available and the observations are made at a particular time. You can convert your time into phase, and this is that phase. And from 0 to 1 is basically one cycle of the neutron star rotation. So it's basically, if a neutron star is of 7 seconds period, then it's basically your one rotation or one cycle of 7.7 seconds. And that information is recorded now in phase, or your period is split into phase information. So as this was an example just to show that this is what we record, the pulse frequency of the neutron star over different times. And this time is in modified Julian date. These are again astronomical units of time, which is equivalent to the calendar date. And here 44,000 means sometime around 1977 or so. So you see the spin frequency of the neutron star was observed of this particular source, 4U1626, was observed over years by different observatories which were there in the X-ray sky, and it sees some sort of a trend. And here you see a steady increase in the spin frequency, and then at certain instance of around 48,000, you see there is a decline in the spin frequency trend. And again, around 54,000, there is an increase in the spin frequency, which is starting. So this sort of very steady behavior observed in this particular source. And these were the pulsophiles which were recorded over these observations. So if you take this point here, let's say, this single point is basically a long observation. It's not a very single, because you see this is time in days. And if you are dealing with the neutron star of a period of 7 seconds, and you have an observation which is a day-long observation, you basically record lot many cycles of the neutron star rotation. So basically, if you play around with this particular data point, you will get something like this. And this is what has been shown here in the right. You study or generate pulsophiles of this point here. What you observe is the pulsophiles like this. And then if you take any data point, so just to mention that phase 1, phase 2, phase 3 are the 3 phases which were split here. So phase 1 is this phase 2 is this declining phase, and phase 3 is again phase where you observe the spin up again. By spin up, I mean the increase in the spin frequency of the neutron star. So each data point or one data point has been expanded into the particular pulsophile. So you see during the decline phase, there was a change in the pulsophile, or the shape of the pulsophile. And then again, you take a pointed observation here, and you expand it into pulsophiles. You observe similar behavior as you observed during this phase, which was spinning up phase, and again during spinning up phase. So these are some sort of interesting cases which we find in our observational study, which allows us to think about what is going around in the neutron star surface, around the neutron stars, or in the accretion disk, or in the magnetosphere, and so on. So that these are the challenges to explain these observational phenomena, that what is causing such change in the pulsophiles or change in the shape, which means some sort of geometry is being changed over time. So these are the things which we are excited about in terms of pulsars. It's just a glimpse or one example, but there are many things which we do in X-ray astronomy for pulsars. Now, coming to the third class of compact objects, which are black holes. So, again, brief history. In 1915, as you all know, Einstein coined the existence of black holes. Of course, by that time, nobody believed that there actually exist black holes. Then there were Einstein predictions about gravity, that what sort of change or behavior he expects when if there exists a black hole. So basically, it's a massive object which will distort the fabric. So you can actually imagine a cloth, and if you place a massive object in that cloth, you will see that it actually basically bends your cloth or fabric. And this sort of distortion is because of the massive object which is placed at the center of your cloth. So you can imagine your universe or your sky as sort of a fabric. And if you have a massive object at the center, it will basically distort your region around that, around itself. So this is some sort of a distortion of your space-time, which can be because of the massive object there in the universe. And these are also known as warps. And this warpage is basically a observable of gravity, or the observations can be like search of such bending of or the existence of warps in the sky or in the universe. Then in 1967, an American physicist, John Wheeler, coined the term black hole. And then there was the first detection of a black hole known as Cygnus X1 in 1971, when the X-ray observatories were launched after the Second World War. So after Second World War, there were rocket flights and so on. So they were looking for X-ray radiation from extrasolar objects in the sky. And then they basically discovered a new class of objects which are known as black holes, and this was known as Cygnus X1. But now the question arises, if these are black holes, they are strong, massive, compact objects with strong gravity, and we believe that no light can escape from these stars, then how do we detect them? If there is no light coming out from these stars, so what is the mechanism or what is the way of observing these objects in the sky? Any guesses? Okay, I don't see anything here. Okay, so if you see this image, can you find a black hole here in the sky? If you just, it's sort of a night sky image. And if you look at a night sky, can you find out where the black hole is there in the sky? Since it's a virtual thing, I think I will not be able to see your expressions or your answers, hear your answers. But most probably, no, we cannot say for sure that where exactly the black hole lies in the sky. But then we do observe or find out the existence of this black hole from the indirect detections. And by now, as I mentioned, one of them is the X-ray binaries or studying these X-ray binary objects. So there is an accretion disk which is formed around black holes, which is basically radiating. And this is one way by which we can actually detect a presence of a black hole. So I have been talking about a class of objects like radio pulsars. Then we talked about X-ray binary system. And then when I mentioned that these X-ray binaries are predominantly emitting in X-rays, so then there is a field which is also emerging because of for the quest or for the study of such objects in the X-ray sky. So there is an introduction to X-ray astronomy. And if you look at this electromagnetic band here, you have all the wave bands covered. You see the X-rays or the temperatures observed here is of the order of 10⁻⁶ Kelvin, and they can go up till 10⁸ Kelvin or so. So, are there questions? You're not audible. I mean, not very clear to me. Okay, so I think there is some background. Okay, so these hot objects in the sky can be studied by space missions, and you cannot rely upon ground observatories to study X-ray observations. And the reason being, the X-rays can be absorbed by the Earth's atmosphere, and there can be no X-rays penetrating the Earth's atmosphere. Hence, we have to fly high above the Earth's atmosphere to catch X-rays or to detect X-rays. So hence we do have space missions, and in the very beginning, we had balloon flights, rockets, but now we have satellites, and they are very sophisticated in terms of instruments on board. And they are actually flown for us. Each satellite has its own science targets or science, basically science-driven motivation, what instruments will be there on board, because of they are driven by science, that what kind of objects we want to study and what exactly we would like to know from the X-ray sky and so on. So based upon that, we develop more X-ray satellites and with instruments or more sophisticated instruments on board. And this is again a range of objects, a range of observatories which are available to us in the current era. As on the top, you can see New Star, which is a NASA X-ray mission, which is very well used by the community, and it's giving excellent results. We have our own Indian mission, which is a multi-wavelength satellite known as AstroSat. You see different payloads here and different instruments marked here. So each payload is dedicated to a specific wavelength, has specific features which are useful for specific sort of study. And then we have IISER, which is again a NASA mission. These are X-ray missions on the top. And then we have optical observatories, which is shown here. These are just example observatories. For optical observatories, we do have plenty, and same applies for X-ray as well. And then for radio, we have Indian observatories, which is GMRT. And then we also have a BLA, which is in USA. So all these observatories together allows us to understand the X-ray high energy astrophysics of this class of objects very well. And we try to exploit data from each of them to understand what is going around in these objects. So this is, don't get scared about sort of randomness observed in this real data. So this is real data from an observatory, X-ray observatory, and on the y-axis again you have count rate, which is intensity given here in kilocounts per second. So it's like a very intense or high intensity object, and you see sort of different sort of behavior, which is or patterns which are observed. And on the bottom, on the top panel, you see for each of this panel, you see some numbers are mentioned. So basically, this is a sort of a roll number. You can imagine it like if you have attendance, you get a roll number in the class. So it's sort of a roll number given to each of these observations. So you basically remember or download data with this sort of registered numbers. So you see for each observation taken at different times, you see different behavior observed. So, and mind you, these are the observations which are taken for a particular type of a black hole in an X-ray binary system. So I mentioned to you that Einstein predicted that there can be sort of a warpage because of the strong gravity objects. And this is observational evidence of such warps which are there in the universe, or warps due to the strong gravity objects in the universe. And they actually tend to change over time. They are not periodic, unlike pulsars. They show random behavior, and we want to understand why such randomness is observed in these observations. And we would like to answer or find basically whether Einstein predictions of general relativity are valid or there are exceptions. So we would like to, basically test general relativity or Einstein predictions by studying these class of objects. And another very interesting observational feature of black holes is they are violent in nature. By violent, I mean at times they can be in a dormant state. They will not say anything. They'll sit quiet. but then suddenly they will show beep in the intensity. They'll basically increase in the intensity, and this is what is observed here. You have an intensity and you have time in days given here. It was sitting ideally for a few days or several days, a few hundred of days, and then suddenly in certain period it decided, okay, I will overshoot, and then you see a huge increase in the signal, and these are known as outbursts. And these are very important phenomena in black holes specifically, because if you zoom in into this single data point, this is what we get. So basically each data point here is corresponding to one image here. So you see each data point is showing a different or revealing a different behavior at different times of a black hole, which means studying the entire outburst of this black hole is very important to us. We would like to understand that what happened at this instance and what happened at the other instance, and then how to connect these two and why exactly it changed over time. So all that things we would like to understand by studying these sort of violent behavior of black holes. And again, this is a short video which will show you about, this is basically a proposed scenario for a black hole, which is being studied. It's a very famous source, J1357. So to explain this image, so as I mentioned, there is an accretion disk around the black hole, where black hole is sitting somewhere at the center. Here you see this orange light coming. So somewhere within that, you have a black hole. And then you see when the companion is radiating, basically transferring matter around this and forming an accretion disk. I'm just replaying it. You see this sort of structures which are there at the center of this, around the center of the black hole. It's basically changing over time. And if you see this signal, which is on the top panel, you see this behavior is also changing as the structure around the black hole is changing over time. So there is some sort of behavior or quasi-periodicity which is observed in the light curves, or by light curves I mean the intensity versus time information. So we try to make a systematic or observational picture or hypothesis, or basically understand or explain the phenomena which is observed in the X-ray universe. So basically, to explain our observations, we try to build models, build pictures which can explain our observational signatures. So by this obscuring structure which was around this black hole, which was changing over time, could actually reproduce these light curves. And this is how we hypothesize that there is some sort of obscuring structure which is present around that black hole, which is causing these sort of dips in the light curves. So this was one example to explain that this is how we explain our black hole existence. I don't know how much time I do have. I think I've already exceeded, but am I allowed to talk something about gender equity as I was requested in my in the email? Am I allowed?
Yes, ma'am. Sure, ma'am.
Okay, thank you. So on this occasion, I was asked if I could talk something about the gender equity scenario in Indian astronomy. And as I'm not sure how many of you are familiar, but we do have a specific group which is known as Working Group for Gender Equity in Astronomical Society of India, which was formed in 2015. And it plays a very important role in bringing or working towards gender equity in Indian astronomy. So there are several roles of this group of members which have been assigned specific duties in this working group. So one of them is to organize Anamani Memorial Lectures on gender sensitization, which attempts to include practitioners from other disciplines in the discourse and have included eminent speakers, which can include science historians, philosophers of science, science journalists, social scientists, as well as scientists. So this particular group organizes periodically talks by all these eminent speakers, and where to bring gender sensitization within the community. And the group of members which constitute this working group of gender equity, they also conduct gender audits of Indian research institutes to understand what is the weightage or number of fraction of student or women students versus women faculty and so on, to understand where are the loopholes or where is the leaky pipeline effect taking place. Just to give you a glimpse of the work done by this particular group of Astronomical Society of India, they conducted a survey within different research institutes in India, and specifically targeting institutes where we have astronomy departments there. And this survey was taken, data was collected from 2013 until 2020, and that confirmed a leaky pipeline effect. By leaky pipeline effect, I mean is, you see, you have almost 50% ratio of women in women doing bachelor's or master's, and then as you move above the ladder, and if you say number of PhD students, it's still okay. You still have considerable fraction of women doing PhD, and but as you move from postdoc to a permanent faculty positions or so on, then you see there is a considerable decline in the number or the fraction of women faculty in astronomy. It's not a Indian problem of India; it's actually worldwide issue. So you see the fraction or the percentage of women faculty overall is about 13 to 16%. And 16% is the very recent data which was collected in 2020, showed some fractional or marginal increase, but that again is not a significant increase. And then there are surveys which are conducted by the WGE group of Astronomical Society of India. So basically, as you might be aware of, Astronomical Society of India has its own conference each year. And during that conference, you have astronomers all across the country gathered where they have the conference and meeting to discuss science results and so on. And there, the survey was also conducted within the participants. And that survey showed, the analysis of that survey showed that 45% of the respondents were women. And on so in the bottom panel, bottom graphs, you can see this. The left plot is showing the survey within the research institutes, which was telling you about the leaky pipeline effect. And on the bottom right, you have the survey results, which was done during the Astronomical Society of India meeting. And you see, this is a woman, which is given by W and represented by W and given in blue, where M is the red, which is the male fraction. So 45 of the respondents were women. And then again, based upon the age, because there was a question that what is your age and so on. So these numbers which are given here are also based upon the age classification. So you see 20 to 29 is in blue and so on. So on this survey analysis of these data, we found that the majority of the scientists which responded, or the women scientists which responded, were within the age of 30 to 50, or the middle age of their career. So they made 70% of your 45% of the respondents of your women category. And what were the other important key results from the survey? The survey indicated that 22% of women reported that they have faced sexual harassment in their departments or institutes, while the almost equal fraction of men and women reported that they know someone who has faced sexual harassment. So which again shows that even if people are not speaking about freely about the sexual harassment, what they face, but still there is a considerable number which they know or themselves have faced sexual harassment, which means it's a big issue. And again, then when they the survey also pointed at that 83% of women perceive that there is a gender discrimination in academic institutions. So while only 43% of men perceived. So by gender discrimination in academic institutions, it's basically, if you recall, that number of respondents were 70% within the age of 30 to 50 years, which means they were already in their early career, or they are already working as a faculty in the institute or so on. So basically at that stage of their profession, they feel that there is sort of gender discrimination. It's not at a school or a college level discrimination. It's basically they are not given the equivalent weightage as a men or men as a faculty. So some 83% of women feel that they have faced gender discrimination when they are in their own institutions. And also one of the major drawbacks, it's the societal effect that it's believed that woman has the responsibility of taking care of the kid. So that is another challenge for a woman in science. And the majority of respondents feel that institutions, if they have the childcare facility, then a part of the burden is taken off, and then they can actually be more focused towards their given responsibilities and duties. So childcare facilities is one of the factor which both men and women have actually, or majority of respondents have found the need of or felt the need of in their own institutions. And just to let you know that childcare facility is one of the mandate now when there are Astronomical Society of India meetings, which helps a lot in the participation of women scientists in these meetings, because then they can bring their babies and this childcare facility can take care of, and they can actively participate in the different activities of the conference. Then most of the respondents felt that gender gap was due to societal constraint, and 91% of women and 85% of men felt childcare facilities in the workplace would reduce the gender gap. And this is linked to the point which I already conveyed. So 80% of women and 70% of men felt that mentoring programs of young women would help reduce the gap. So there's some sort of mentoring programs where MSc or PhD students can be, basically there can be awareness programs, or there can be some sort of teaching programs which can help in mentoring young women and helps in reducing the gender gap. So most felt that these sort of open discussions on gender discriminations are needed. As I mentioned, that majority of people who have faced sexual harassment do not open up, just because of our, sometimes because of our society, how we are brought up in the society, and such open discussions are really needed to understand where the problem is and how we can get rid of it. So based upon this survey, of course, there are future activities which are to be planned, and those are some of the future activities which were decided or discussed by the WGE members was, of course, there is a marginal increase in the faculty ratio, rising from 13 to 16%, but then the survey also shows that these efforts have to be continued. We cannot stop right now, because it's not the time to stop, because we are still in the very early phases where we need where there is an urge to increase the voice or raise our voice to have equity in science, or gender equity in astronomy or science. So they plan to continue this Anamani lectures, which is for gender sensitization. And they also plan to conduct nationwide surveys, yearly surveys, so that to understand whether there is a continuous increase in the fraction of women in faculty, or then it again shows some sort of a random behavior or a dip or anything, to understand, to have evidence-based intervention. So because when you have data collected, then you will be having a evidence that there is something going wrong in our the way our institutions are working, or where we need a change. So all those activities can be planned based upon our data which is being collected. So they are planning to have regular conducts in different institutes. And these are some of the important websites from where I have collected data from. And this particular data was also presented, as Madhurima mentioned in the beginning, that we both were together in one of the IUPAP conference, which took place in Australia, which was specifically targeting this gender equity issues. So these, there was a poster which was presented during the conference. So this is the website and for that conference, and this is the website of the WGE group members and the various activities done by these members of Astronomical Society of India. And as you all know, this is the ASI website, so you can always visit, and you can also watch the videos which are being recorded during these Anamani lectures, and they are freely available there on the YouTube channel, and you can actually watch and see how the discussions takes place to warm up the community and find out ways out. And with this, I would say thanks, and I'm happy to take questions.
Thank you, ma'am.
Thank you.
I request all the participants to type your questions in the chat box, if any. Ma'am, there are some questions in the chat box right now.
Okay, let me.
Shall I read them out?
Okay, that will be helpful, but I will also try to see if I can read them. So I see the first question, what is the most common stellar remnant? Does universe favor a particular type of a star? If so, why? So I think this is a question by Devika, where she is saying that there is a what is the most common stellar remnant? So the answer to this is not that there is a common stellar remnant. What type of stellar remnant will be formed depends upon the initial mass of the star. So if you have a very massive star, and you do have a lot of massive stars there in the universe, so then they can end up as a neutron star or a black hole. So both the probability of forming a neutron star or black hole depends upon the mass of the star, which will undergo supernova explosion. So the probability is mostly relying upon the density or the number of stars available and what is the mass of that star. So as I mentioned, that there are main sequence stars or the sun-like stars, and that will end up as a white dwarf. So each star has its own fate, and hence the probability is not like a common scenario. It will have their own definite end cycle. I hope I have answered this. So are pulsars and magnetas related, and how does a neutron star evolve to be a magnetar or a pulsar? It's a very good question. So basically, magnetas are also a special type of pulsars, and here the source of energy is not rotation but the magnetic field of the neutron star. So as I discussed two types of pulsars in this talk. One of them was a rotation powered neutron stars, which are taking or extracting energy from the rotation of the neutron star, whereas magnetars are the stars where it's basically the magnetic field generating, it's helping in radiating in X-rays or radiating energy. So this linkage of different types of stars is a very it's an open challenge right now within the community, that how the magnetic field strength decays, or because when you have a freshly formed neutron star, you have strong magnetic field, and then how does that magnetic field decay over time and so on. This is ongoing in the state of the art research or the open questions to us, and there is something I'm not sure if you're familiar with. There is some sort of a diagram which is known as PP dot diagram, basically where we record different types of pulsars based upon their magnetic field and spin period and rate of change of spin period, and then place them in that plot versus magnetic field. And this plot is to understand how one type of or one class of pulsar is linked to the other. For example, there are some sort of pulsars known as recycling pulsars. So they are pulsars where recycling by it means they spin up by the accretion phase. So they undergo transition. At one phase, they are radio bright, and the other phase, they are X-ray bright. So there is a link between when there is no accretion, it becomes radio bright, and then when there is an accretion, it becomes X-ray bright. So there is a linkage between these two classes of the same object, but when observed at different times. And in the same way, the magnetic field is also evolving over time. And how that magnetic field is evolving is a challenging question. And yes, we all are interested to understand, and hence we have new missions, not only in X-rays, but in radio, like SKA also, where we will be able to hunt more systems which are fainter, like magnetars, and try to understand this linkage. Are the pulsar rotation axis and magnetic field axis aligned? Okay, so if they are aligned, then there will be no pulsations. Because they are misaligned, that's why we do observe the pulsations from these objects. And how long does a supernova last, or how long will it remain bright? Okay, so the supernova explosion can last for a few days to few months, and so they outshine the entire galaxy where they are erupted or they blast. So they can last for a few days, and they can outshine the sky for a few days to few weeks, and a few months in some cases if it's super bright. Why do we expect strange quark matter to exist in the core of the neutron star? I didn't touch upon this particular topic because this is a very important question, and unlike pulsars, we do have low magnetic field neutron stars as well. As I mentioned to you, that magnetic field of the neutron star also changes over time. And there are class of neutron stars where the magnetic field is not of the order of 10 to the power 12 Gauss, but it's of the order of 10 to the power 8 to 10 to the power 9 Gauss. So in this low magnetic field, consider relatively low magnetic field neutron star. This is again not low compared to the magnetic field of the Earth of few Tesla. But this magnetic field is lower compared to 10 to the power 12 Gauss, or 10 to the power 13 or 14 Gauss in the case of magnetar. So this class of neutron stars are very helpful in understanding the supranuclear density within the cores of the neutron star. So you form the equation of state models where basically it's a pressure and the density balance equations. So from the observations, we try to understand or measure the mass and the radius of the neutron stars. And when you have observations which gives you mass and radius of the neutron star, then there are nuclear models and strange quark models, which are particle physics driven models, which try to explain the equation of state or the pressure density relation within the cores of the neutron star. You basically have those theoretical models. These are theoretical models. We do not have observational evidence whether there exists a quark matter or a strange matter within the cores of the neutron star. When you basically measure observationally mass and radius, then you have a mass radius relation, which is given by this equation of state models, which are based upon the nature of the material within the cores. And if your mass and radius measurements, which are observational evidence, they fit those curves, which were predicted by this quark matter models or strange matter models, then basically you validate that there could exist a quark matter, or rather, I would say, in other words, that this particular model explains our observations. It is not that every neutron star will have this strange quark matter there in the cores of the neutron star. But in that particular observation, a particular model is being favored, because you cannot get into the cores of the neutron star. So there are several models which are existing or theoretically available to us. But what is challenging is to validate those models, or to accept or refute certain models. So this is our job, observation, as an observational astronomer, to validate or to refute or accept a particular model. I hope I have tried to explain you what in simple words. Let me know if it is unclear.
Yes, ma'am, it's clear.
Will the stellar remnants formed after a hypernova be any different from supernova? I mean, okay, so stellar remnants formed after hypernova. So again, it's again an end product. They will be of the similar nature. They will be a compact object only after the end product of the stellar after the hypernova explosion. Okay, so how big a black hole can be? So as I mentioned, or in the very beginning of my slides, I gave you an expression of the Schwarzschild radii, which is given by 2 gm by r square. So this is the virtual radius of the or the fictitious radius of the black hole, or give a size of the black hole or a fictitious size of the black hole. So it depends upon the mass of the black hole that how big or how small it will be. It depends upon really upon the mass of the black hole. So as you know, it's gm by r square. So if it's very massive, it will be really condensed and compressed black hole. Using radio astronomy while observing a specific object, how do you identify and remove the unnecessary noise? I'm not a radio astronomer as such, so I will not be able to give you very technical details about the radio astronomy as such. But since it's a general class is astronomy and we do X-ray observation, so in the case of how do you identify? So in terms of identifying an object, each object is being specified coordinates in the sky. So this is a general question for observational astronomers. Basically, it's a RA index, which is right ascension and declination. So it's basically sort of a positional coordinates of an object. So if you find an object at that particular coordinates in the sky, then you, if it's a well-known source, then you identify it as a particular class of object or a particular object in the sky. Talking about removing unnecessary noise. So in X-rays, I'll be not particularly talking about radio astronomy, but because there can be different ways of eliminating noise. But in terms of X-rays, you basically have a background estimation also, the background sky. So you have observations not only of the object, but also of the background. And then one way is that, and also your detector can have its own background. So you basically illuminate or model that background of the detectors or calibrate your instrument also before launching, and to develop those models of the background models for those detectors. And this is another way. And then sometimes when you have some certain sort of detections, let's say when we are dealing with the pulsar, and if it's an unknown source, if it's a known source, you know the periodicity of a pulsar. Let's say for a pulsar of 1626, which is 7 seconds pulsar, then you basically know that it's a 7-second period. And if you look at the light curves, or the light curves, which means intensity versus time. So if you see a signal repeating every 7 seconds, you can call it as a pulsar, and you know it's a particular pulsar. But what if it's a unknown source? Then you have to take care of algorithms to find out whether it's a true signal or it can be just a spurious signal because of some sort of background noise or some funny behavior in your detectors. So then there are algorithms, which is more technical, not be able to explain right now in very briefly, because there are some technical steps how to find out whether it's a true signal or not. Is predicting the future of a star completely dependent upon its mass? So as I mentioned, it's a life cycle of a star in the very beginning. So roughly speaking, it depends upon the mass of the star, whether it will undergo a supernova explosion or it will undergo planetary nebulae, form a planetary nebulae also. So partially it's yes, but again, these are unpredicted. at times and as you see, I'm not sure if you have taken basic astronomy courses, then you also have something called that HZ diagram, which is giving you a I mean, basically, it's a sort of a diagram where you have a magnitude versus your spectral types. And it basically links between different types or different classes of stars. So basically, we predict the life cycle of a star based upon that HZ diagram also. So I think the basic astronomy courses can be able to answer you that question. How bright can a supernova in our own galaxy get? So as I mentioned in the beginning, it can be as bright as 10⁻43 ergs per second. Will it outshine other celestial bodies in the night sky? I mean, yes, it can, but the only thing is whether be able, it also depends upon the distance, because the supernova explosions are not very frequent events. They occur occasionally, and if you talk about a particular galaxy, you expect maximum of 1 or 2 events in a 50 years or so. But now we have so many galaxies in our universe, then we observe, observational astronomers observe a few hundreds of supernova explosions. But then whether you will be able to see that brightness depends upon how far is that galaxy from us. They will be luminous, they will be outshining, but whether it's the brightness, I mean, brightness in terms of whether we'll be able to have enough counts or enough emission coming towards us, this depends upon the distance distance from us. So I think these were the questions which I found in the chat box. If there are any more, let me know.
Ma'am, I think there are no more questions. So thank you so much for patiently answering all our doubts.
No problem. Thank you.
Yes, ma'am. I hand over the session to Asmita for a vote of thanks.
Sure. Thank you.
Thanks a lot, ma'am.
Thank
So
you.
that was a wonderful session. We have got a lot of information from you.
Thank you.
We were engaged throughout the session. Thanks.
Glad to hear
thank
that.
you, Aru. Thanks a lot.
Thank you, Madhurima.
Thank you, ma'am.
Yeah. I'll catch up with you later on. Bye.
Sure. Bye. Bye.
Without women, we cannot think about the society. 50% of it.
Okay. So, if there are no questions, am I allowed to leave the session?
Yes, ma'am. Thank you so much.
Okay. Thank you, Devika. Thank you all.
Devika, can I end the session for everybody?
Yes,
oh, I think Asmita should. I think Asmita should.
So here we conclude the session. I thank all of you who have joined here, and thank Madhurima for arranging this session. Thank you.